Have you ever found yourself wanting to show the displayable hex values for a series of byte data from a COBOL program? Here's an example. Error code from XYZ's utility is 5894. 5894 was not in the list of the errors for the XYZ's utility. After looking at the code, it clicked that the field that held the value of 5894 was defined as pick S9 for binary, showing the hex value for 5894 is required. The hex value of 1706 was in the list of errors. In this video, we discuss a small assembly program using the translate 1 to 2 instruction to convert data into hex characters. Howdy! Welcome to another episode of Dinosaur Parkour, Faster, Better Mainframe Programming. I'm your host, Chris P. Fide. It is a short utility. There are a bunch of comment lines as shown here. These comments explain how to invoke the utility from a COBOL program. There are three params being passed to the utility. Param 1 is the length of the input byte to be translated. Param 2 is the input bytes or field. And param 3 is the output field for the hex value. Line 2 declares the code section named byte to hex. Line 3 says that this program is to use 31-bit addressing. Line 4 declares that the system can load this program either in 24-bit or 31-bit address space. It cannot be loaded above the bar in 64-bit address space. Yeah, I know. The any is confusing in this case. Any existed when the valid addressing modes were 24 or 31. In other words, any existed prior to 64-bit addresses being valid. Line 22 through 35 is setting up what is known as standard linkage for a program that uses 24 or 31-bit addressing. Line 25 saves R1 by moving it to R11. R1 should be pointing to the list of addresses for the three params expected by this utility. Currently, there is no logic to validate that the parameters were passed. The get main is commented out, but if it was live, it uses register 1, which is why register 1 has to be saved. Since line 30 through 35 are commented out, this is not exactly standard linkage. Byte to hex is not defined in the save area. This is being done to improve the speed of this utility. Since this program does not define a save area as part of the linkage convention, it cannot safely invoke another program. There is code in the exit section to release the save area that is commented out. Acquiring and releasing the save area uses a small bit of CPU and time that I want to eliminate. The translate 1 to 2 instruction, or TROT, is being used. This is the translation table. The table was created with a ret strip to reduce the chance of a coding error. Hex 00 translates to character 00. Hex C1 translates to character C1. Hex F0 translate to character F0, and hex FF becomes character FF. This program converts a byte into its 2-character displayable hex value. If the ETF2 enhancement is installed, the table can be double word aligned. Line 96 forces double word alignment. If the ETF2 enhancement is not installed, the table has to be aligned on a 4K boundary, which I would have to figure out how to do. Just FYI, in case you're working on older hardware. When you read about the translate 1 to 2 instruction in the POPs manual, it describes 4 instructions at once. The POPs manual describes translate 1 to 1, 1 to 2, 2 to 2, and 2 to 1, which can be confusing. It was for me. So I started taking notes, which are shown in these comments. Line 51 and 53, I have the S in paren because based on the instruction, those are either 1 or 2 bytes. TROT uses a total of 5 registers to perform its function. But when coded, only two are named directly as part of the syntax. I picked R2 and R4. Register 1, or operand 1, is an even-odd pair of registers, so I decided to use register 2, and the odd portion is 3. For register 2, or operand 2, I decided to use R4. Register 0 and 1 are also used by the TROT instruction. There is a third operand, or the mask, that is optional. However, it will be used. It controls if translation should stop if a specific function characters are found. We do not want that. We want to translate the entire input field without stopping. R2 is the even register for operand 1, and it points to the address of the hex output field. R3 is the odd register for operand 1, and it is the length of the input field to be translated. R4 is operand 2, and it is the address of the input data, or the byte to be translated. R1 points to the address of the translation table that we looked at a couple of minutes ago. R0 is the comparison or test character that triggers the instruction to stop. This will not be a factor for two reasons. One, we're going to use the mask, which is operand 3, to turn the comparison off. And two, we're going to clear register 0 to be low value. Thus, a comparison character of low value plus low value is not in the translation table. The translation table only contains characters 0 through 9 and A through F. This is a dset, or a dummy section, that defines the three input forms. The bottom half of the screen shows the example of how the call appears in a COBOL program. According to the notes, register 2 is the output field or the hex data, so parm 3 is loaded into register 2. Register 3 is the length of the input, which is parm 1. Register 4 is the input data, or byte to be translated, which is parm 2 on the COBOL call. Now, the news is assigned to register 11, which is where the pointer to the parm was saved, can be dropped. It is the best practice to drop musings as soon as possible. Load the address of the translation table into R1. Clear R0, which makes the comparison or test characters hex 00, hex 00. Line 67 executes the TROT instruction. TROT sets 3 condition codes. The condition code is 2 bits. If the condition code is R1, or condition code of 3, the TROT instruction needs to be performed again. When the TROT instruction is executed, the CPU determines the number of characters to process before stopping. Maybe it needs a break. A joke. It's most likely doing so to allow other work to be able to use the CPU for those times when you're translating a very large series of bytes. Re-execute the instruction without changing the register. Condition code of 2 is not used by TROT. Condition code of 1 is set when the comparison bytes in register 0 matches the function bytes from the translation table. Condition code 1 should never occur for this program. A, the comparison is turned off, and B, the test bytes in register 0 are not in the translation table. Once the translate 1 to 2 instruction complete with a condition code of 0, the utility is finished. It is time to wrap up. Since the save area was not set up for this program, the lines related to it are commented out. Lines 64 and 66 were part of a test to see if condition code 1 could be triggered. It was. This is a quick program to show how the utility works. Line 28 and 29 define the input and output field. Channel name is 20 bytes. W hex is 8,192 bytes. I made it much larger than required. When this test program starts, that field is initialized with 8,192 tildes. Line 38 to 41 invoke the utility. The by value clause tells the call statement that a numeric value is being passed directly. the value is stored in the binary full word for the parm, not a pointer to another field. In a 31-bit COBOL program, the length of clause has an implied pitch clause of 99 binary. Reference pointers to the channel name and W-hats are passed. This time, pointers to the field are stored in the full words of the parameter list. The channel name is displayed. The hex data is displayed. Only 40 position needs to be shown, but the program displayed 45 positions of W-hat. There is a loop to spread the channel name out. A space is inserted between each character of the channel name. Then the 40 position of the spread name and W-hat is displayed. This is the result. Line 4 is showing the tildes at the end. In the program, W-hat was filled with tilde symbol. The TROT instruction only uses 2 times the input size. Channel name was defined as PIC-X20, so only 40 bytes of W-hat were impacted by the translate 1 to 2 instruction. The spread out loop makes it easier to see the relationship between the channel name and its hexadecimal value. Uppercase letter D is code point C4. Lowercase letter O is code point 96. And uppercase P is D7. There you have it, a quick utility to convert bytes of data to their hexadecimal value. This has been another episode of Dinosaur Parkour, faster, better mainframe programming. Thank you for listening. Please consider subscribing to the Dinosaur Parkour channel if you found this video useful. There should be a subscribe icon on the screen.